You have not moved from this spot in the last 60 seconds. And in that same 60 seconds, you travelled 17 miles, carried by a planet that has never once stood still since the day it formed. In 2011, astronomers confirmed something almost nobody expects. A black hole 7,000 light-years away is spinning at nearly the fastest rate physics allows. That black hole completes over 800 rotations every second. Every spiral galaxy ever mapped spins fast enough at its edges to fly apart under its own visible gravity. And Earth itself is losing 1.8 milliseconds of spin every single century. Tonight, we go through the invisible force that taught a cloud of dust how to spin, while your own planet is quietly losing its rotation, the black hole called Cygnus X, one that turns faster than physics thought possible. And the Sloan survey that found galaxies across the sky might all be turning the same way for a reason nobody has yet explained. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. You are lying still. Your breathing has slowed. Your eyes have stopped moving across the room. And in a few minutes, they will close on their own. And underneath all of that stillness, you are being carried sideways through space at roughly 1,000 miles an hour, spinning with the surface of a planet that picked up its rotation before there was any life to notice. Here is a question worth asking before we go any further, and it doesn't have a clean answer. Why does the Earth spin at all? Not why does it spin at this particular speed? Why does it spin in the first place? A ball dropped in still air doesn't start turning. A puddle doesn't spontaneously begin to swirl. Left alone, matter tends towards stillness, not rotation. And yet every planet, every star, every galaxy we have ever pointed a telescope at is turning. Rotation isn't the exception in this universe. It is very close to the rule. Scientists confirmed decades ago that this can't be coincidence, and most people who have watched 100 space documentaries still don't know the actual mechanism. It isn't magic, and it isn't the leftover force of the Big Bang pushing things around, the way people often assume. The Big Bang wasn't an explosion into empty space, and it left no outward push capable of spinning anything up. The truth is stranger and, in its own way, more intimate. The spin in your planet, in your star, in the galaxy holding both, was assembled the same way a whirlpool assembles itself around a bathtub drain, from motion that was already there, amplified by nothing more than falling inward. We are going to trace that amplification tonight, from the smallest particle in your body to the largest structures we have ever mapped, and by the end you'll understand why the universe hasn't been able to stop turning since the moment it started to fall. So, before we go any further, hold 5 questions in mind. You'll have every one of them answered before the night is through. Why does a collapsing cloud of gas start turning at all with nothing there to push it? What is actually stealing the spin out from under your own feet, one heartbeat at a time? How fast can a dead star turn before physics itself calls a stop to it? Can a black hole really drag empty space around itself the way a whirlpool drags water down with it? And why would galaxies that have never touched each other, separated by hundreds of millions of light years, seem to agree on which way to turn? Whether that turning is only physics doing what physics does, or something closer to a signature written into the fabric of everything, is a question this documentary will not fully resolve. We are going to sit inside it. Now add one more layer to the 17 miles you've already travelled this past minute. While your patch of Earth carries you sideways at roughly 1,000 miles an hour, the planet itself is racing around the Sun at 67,000 miles an hour. Now add the Sun's own motion, the entire solar system, you included, orbiting the centre of the galaxy at nearly 500,000 miles an hour, a lapse so vast it takes 230 million years to complete just one. And the galaxy itself is not sitting still either, falling through space toward a gravitational anomaly so large astronomers only ever agreed to call it the Great Attractor. You have never, in your entire life, been still for even a fraction of a second. Every measurement of stillness you've ever felt was borrowed, temporarily, from something underneath you that was already moving. But even your own body carries proof of the small mechanism behind all of it. Somewhere in a hospital right now, a figure skater's trick is happening without any skater in the room. Picture a cloud of gas and dust, cold and dark, light years across, long before there was a sun or an earth inside it. Not because it was pulled by something spinning, because it wasn't spinning at all. Not in any obvious sense. It was drifting, turbulent, its billions of particles moving in every direction at once, colliding, curling, cancelling each other out almost perfectly. Almost, that word almost, is where everything begins. No real cloud of gas in this universe has particles moving in perfectly opposite, perfectly cancelling directions. There is always a residual drift, a slight net rotation buried in the noise, too small to measure, too small to matter. At first, then gravity starts pulling the cloud inward, and something changes that has nothing to do with force and everything to do with bookkeeping. Physics keeps a ledger called angular momentum, and it does not allow that ledger to go to zero once it holds any value at all. As the cloud collapses, as its radius shrinks, that tiny leftover spin has nowhere to go. It has to speed up to conserve the same total rotation in a smaller space. A slow, imperceptible drift across light years becomes a fast, decisive spin across millions of miles. Nothing pushed it, nothing forced it. It only had to fall. The numbers involved are almost comically lopsided. A cloud like this, before collapse, might take several million years to complete a single, barely detectable rotation. Slower than the hour hand on a clock that's already slower than any clock you own. Shrink that same cloud down by a factor of 100,000, packing the same rotation into a radius that small, and the star forming at its center can end up completing a rotation in a matter of days. Nothing added the energy to make that happen. The collapse alone was the entire engine. Here's what those numbers don't tell you. This isn't a special rule for star-forming clouds. It's the same ledger a diver uses pulling into a tuck, the same ledger water uses spiraling into a drain, the same ledger a dying star uses collapsing into a pulsar spinning hundreds of times a second. The universe has exactly one accounting trick for rotation, and it applies at every single scale we have ever measured, from a proton to a supercluster of galaxies. Astronomers have actually watched this happen, not just calculated it. Radio telescopes trained on a young protostar called L 1527, wrapped in a cloud roughly 450 light-years away, have measured the rotation of infalling gas directly, slower and looser farther out, tightening and speeding up the closer it falls toward the newborn star at the center, exactly the way the ledger predicts. The cloud that starts this process can take 100,000 years to fall. The disk it becomes takes only a few hundred to start spinning fast enough to flatten. Not a coincidence, not a metaphor stretched to fit the facts. The same law, doing the same thing, from the smallest object you'll hear about tonight to the largest. And it started working on the material that would become you, roughly 4.5 billion years before you existed to notice. 4.5 billion years ago, the collapsing cloud that would become our solar system had condensed enough to catch fire in its center, and the outer material was still falling inward, still carrying that same conserved spin, still speeding up as it fell. Almost everything in this system, the planets, most of their moons, the asteroids in the belt, inherited a piece of that original rotation and still turns in the same direction around the sun today. It's a fossil when you look at a single, unremarkable fact that Venus turns backward. You're not looking at a boring anomaly. You're looking at the one planet whose formation went differently, a scar from a collision sitting inside a system where everything else still remembers the same original spin. But the sun itself doesn't spin the way you'd expect a star built from a fast collapsing cloud to spin. Here's the part that changes everything. The sun rotates far slower than the conservation law predicts it should, once you account for how much of the cloud's original spin it should have kept. Something bled that speed away before the star finished forming. Magnetic fields threading out into the surrounding disk, carrying angular momentum outward, the way a tether flings a weight further from a spinning platform. The planets, in a strange sense, took on some of the spin the sun was never allowed to keep. Hold this number, because it doesn't sound real the first time you hear it. The sun holds nearly every scrap of mass in this solar system, somewhere north of 99% of it, and yet it holds barely 2% of the system's total spin. Jupiter alone, a planet with less than 1,000th of the sun's mass, carries most of the rest. The star that dominates everything by weight is, by rotation, almost an afterthought next to its own planets. And the sun isn't finished losing it. Every second, it sheds roughly 1 million tons of material into space as solar wind, carrying trace amounts of that leftover spin outward with it. Over its 10 billion year life, this slow bleeding has already measurably slowed its rotation compared to when it was young. It will keep slowing until, one day, billions of years from now, whatever remains of the sun stops turning the way it once did. The sun doesn't even turn as one solid piece, the way Earth does. Because it's a ball of plasma and not solid rock, different latitudes are free to rotate at different speeds. Its equator completes a full turn in about 25 days, while regions near its poles take closer to 35. Stand at the sun's equator, if you somehow could, and the pole would be visibly falling behind you within a single month. No solid planet is allowed that kind of internal disagreement. A star, it turns out, doesn't have to keep its own promise to itself. Even your own star, the one warming your skin every day of your life, is slowly forgetting how it was born. The planet under you is doing the same thing. On a scale you can actually feel. You just haven't been alive long enough to notice. Here's what almost nobody completely misunderstands about this, until it's explained plainly. The moon is stealing Earth's spin, a little more every single day. The moon's gravity drags on Earth's oceans, raising a tidal bulge that Earth's faster rotation pulls slightly ahead of the moon itself. That bulge, in turn, pulls back on the moon, and the pull isn't free. It costs Earth some of its rotation, transferred outward the same way the sun handed spin to its planets. The bill for that theft is precise. Earth's day is getting longer by about 1.8 milliseconds every century. It sounds like nothing. Stay with that for a moment. 600 million years ago, when the first animals were figuring out how to build shells, an Earth day lasted less than 22 hours. The extra 2 hours since then didn't appear from nowhere. They were paid, second by fractional second, to a moon that used to orbit much closer and now drifts 1.5 inches farther away every year, carrying stolen momentum with it. The moon is, in the plainest physical sense, running away with a piece of your planet's spin, and it has been doing it since before there was a you for 400 million years running. We didn't have to guess at this from orbital mechanics alone. Fossil corals hold the receipt. A coral grows a new microscopic ridge on its skeleton every single day, the way a tree lays down a ring every year, and geologists counting those daily ridges in 400 million year old fossils keep landing on the same uncomfortable number. About 410 ridges per year, not 365. Not because those ancient years were longer, because the days inside them were shorter. The planet was turning faster, the same year taking more, quicker spins to complete one lap around the Sunday. This doesn't end quietly, either. Given enough time, tens of billions of years, longer than the sun has left to live, the transfer would eventually run its full course. Earth's day would stretch to match the moon's orbit exactly, both bodies locked face to face, one side of Earth staring permanently at one side of the moon, the way Pluto and its own moon Charon already do today. we will never see it. But the process pointing toward it is running under your feet at this exact moment, and has been for 4 billion years. But there's a strange asymmetry buried in this transaction, and it's the reason astronomers keep watching leap seconds. The theft isn't perfectly smooth. Earthquakes redistribute mass toward or away from the planet's axis. Melting ice sheets shift billions of tons of water from the poles toward the equator. Even the core sloshing beneath your feet changes the rotation by fractions of a millisecond, unpredictably, in ways nobody can forecast a decade in advance. We'll come back to what that unpredictability might mean for something much larger than Earth. For now, hold this. Even the most reliable clock in your daily life, the length of a day, is not fixed. It is a slow, one-way payment, and the moon is the one collecting. Now take the same ledger that slowed the sun and shrank a collapsing cloud, and apply it to something that has already run out of fuel. When a star roughly 10 times the mass of the sun exhausts its core, it collapses in less than a second, from a sphere wider than the Earth's orbit to a solid core barely 12 miles across, the width of a city, holding more mass than the Sunday. Nothing about this collapse pauses to consider the star's original, leisurely rotation. The angular momentum ledger doesn't negotiate. Whatever spin the star's core carried, however slow, has to be conserved into a radius tens of thousands of times smaller. The result is a neutron star, and some of them are measured spinning over 700 times every second, not 700 rotations a year. A second. A city-sized ball of matter so dense that a teaspoon of it would outweigh a mountain, spinning fast enough that a point on its equator moves at a meaningful fraction of the speed of light. Pause on that. A star that once took weeks to turn, once now completes 700 full turns before you finish reading this sentence aloud. Astronomers call these objects pulsars, because the spin sweeps a beam of radio waves across the sky like a lighthouse, and we only see it flash each time the beam crosses Earth. The first one was mistaken, briefly and seriously, for a signal from another civilization. The beat was that regular, that mechanical, that impossible seeming for something built by nature alone. It wasn't a signal, it was gravity, doing arithmetic on a scale that has no patience for anything as slow as a human clock. But even 700 rotations a second isn't the ceiling. Somewhere past this speed, physics draws a hard line, and what enforces that line is stranger than the spin itself. Here's the question that keeps physicists awake about objects like this. Why don't neutron stars spin even faster, given how extreme the initial collapse can be? The answer is that there is an actual speed limit, and it isn't arbitrary. If a neutron star's surface tried to rotate fast enough, the outward force at its equator would exceed the gravity holding it together, and the star would simply fling material off itself, tearing its own edge away rather than continuing to accelerate. For a typical neutron star, that limit sits somewhere around 1,000 rotations per second. Go faster, and the object doesn't spin faster. It falls apart. This isn't a special rule invented for dead stars. It is the same tension holding a spinning coin down and the same tension holding a fast-spinning centrifuge intact, scaled up to an object where falling apart means shedding matter denser than anything else in the observable universe. Spin fights gravity everywhere it exists. Usually gravity wins comfortably. In a neutron star, the contest is closer than almost anywhere else we've measured. The record holder sits close enough to that ceiling to make the point on its own. A pulsar catalogued as PSRJ 1748-2446 AD, found in 2004 inside a dense cluster of ancient stars, spins at 716 times every second, close enough to the theoretical breaking point that some models of its interior put it within shouting distance of shedding its own surface. Nobody has found one that beats the limit. That, on its own, is a kind of confirmation. The ceiling isn't just mathematics on a chalkboard, it is a line the universe has never once been caught crossing. And there's one place where the contest tips even further. where the thing doing the spinning isn't made of matter you could touch at all. Here's where the story stops being only about matter and starts being about the shape of space. In 1918, two physicists named Lenzer and Thirring worked out a strange consequence of Einstein's equations. A massive rotating object shouldn't just sit in space and spin, it should twist the space around it. The way a spoon dragged through honey drags the honey along with it. Not metaphorically. The equations said space itself, the coordinate grid that everything else moves through, gets pulled around a spinning mass. For decades, this was considered nearly untestable, the effect too small to measure around anything we had access to. Then, in 2011, after more than 4 decades of preparation, a satellite called Gravity Probe B confirmed it directly, measuring the Earth's own comparatively gentle spin, dragging space around itself by a fraction of an arc-second per year. A number so small it required gyroscopes more precise than any built before. To catch a number that small, engineers had to build the roundest objects human hands have ever made. 4 quartz spheres, the size of ping-pong balls, polished so evenly that if one were scaled up to the size of the Earth, its tallest mountain would rise no more than 8 feet. Any imperfection larger than that would have buried the signal in noise. They spent 4 decades perfecting a sphere precisely so they could watch it get dragged, almost imperceptibly, by the spin of the planet beneath it. If Earth's slow rotation drags space measurably enough to need the roundest objects ever built to catch it, consider what a black hole does, and consider that this same faint dragging is happening under you, right now, too gently for you to ever feel it. A black hole, called Cygnus X, 7,000 light-years away, was measured the same year, 2011, spinning at more than 800 times a second, over 95% of the absolute maximum rotation speed. Physics allows for an object of its size. At that speed, the black hole doesn't just curve space around itself. It drags the space immediately outside its horizon into a forced rotation, a region called the ergosphere, where nothing, not light, not matter, not empty space itself, is permitted to stand still, not gently curved, not slightly disturbed, forced, dragged, made to spin whether it wants to or not. There's a strange side effect to being dragged that violently. Physicists have shown, at least on paper, that a spacecraft daring enough to dip into that forced region and split itself in 2, flinging one half deeper toward the black hole while the other half escapes, could come away with more energy than it went in with, drawn out of the black hole's own rotation like a toll charged in reverse. Nobody has built the spacecraft, but the black hole's spin, in principle, is a reservoir of energy sitting in plain sight, gifted by nothing except the fact that it never learned how to stop turning. Nothing has to spin, and yet, somehow, everything does. Even the fabric that spin is supposedly moving through. We know the mass of Cygnus X, one with unusual confidence, for a reason that has nothing to do with rotation, and everything to do with a decades-long argument between 2 of the most famous physicists of the last century. In 1974, Stephen Hawking placed a bet with a fellow physicist named Kip Thorne, the wager, that Cygnus X1 did not contain a black hole. This is stranger than it sounds, because by 1974, Hawking had already built much of his career on the physics of black holes. He wasn't betting out of genuine doubt. He described it later as an insurance policy. If black holes turned out not to exist after all, if his life's work collapsed under him, at least he'd win a bet. He was hedging against his own discovery. The evidence took 16 years to become undeniable. Cygnus X1 is a binary system, a visible blue supergiant star orbited by something unseen, something dense enough to pull streams of gas from its companion into a swirling disk that shrieks in X-rays as it falls. By measuring the visible star's wobble, the slight, rhythmic pull of an unseen partner on an orbit that takes 5.5 days, Physicists narrowed the invisible object's mass down to somewhere around 15 times the mass of the Sun, packed into a region smaller than a city. No known physics allows that much mass in that little space to be anything except a black hole. In 1990, Hawking conceded. He broke into Thorne's office while Thorne was travelling and signed the bet certificate, settling a debt that had cost him a subscription to a magazine he found faintly embarrassing to receive. What makes the story worth telling isn't the joke at the end. It's that Hawking, arguably the person on Earth with the most invested in black holes being real, chose to bet against them anyway. Not from doubt, but from an old scientist's habit of never fully trusting a universe that keeps its best evidence indirect. Cygnus X1 itself has never been seen. It has only ever been inferred from the wobble of a companion star and the scream of infalling gas. Hawking's bet, in a strange way, was a bet on how far indirect evidence should be trusted before you call something settled. 16 years of data settled it for him. It would be another 29 years before anyone photographed a black hole directly at all. In 2019, a network of telescopes spanning the entire planet, synchronized to the same instant, finally captured an image of the shadow cast by a black hole in a distant galaxy called M87, a dark circle ringed in glowing, superheated gas, the first black hole any human eye has ever actually seen rather than merely calculated. Cygnus X1 wasn't the one in the photograph, but every bit of confidence in that photograph traces back to decades of exactly the kind of indirect argument that finally convinced Hawking to hand over his subscription. This is the last piece you need before the picture gets bigger than any single object. So now we have the mechanism, a mass that conserves its rotation as it falls, whether it's a cloud, a star, or the space around a black hole. But on its own, conservation only explains why a single object keeps spinning once it starts. It doesn't explain why almost every collapsing thing in this universe, at every scale, falls into the same specific shape. Now consider a question so basic it usually goes unasked. When something collapses under gravity, why does it flatten into a disk instead of just becoming a smaller sphere? A cloud with zero rotation would collapse into a ball, symmetrical in every direction, because gravity itself pulls equally from all sides. But we've already established that no real cloud has zero rotation. There's always a residual spin, and rotation breaks that symmetry in one specific, unavoidable way. Along the spin's axis, nothing opposes the inward fall. Material collapses freely toward the equatorial plane, but around the spin's equator, the same rotation that's being conserved and sped up also generates an outward flinging force, fighting gravity's pull inward. The result is a flattening, the same shape appearing whether you are looking at a spinning lump of pizza dough thrown into the air, the rings encircling Saturn, the disk that built our entire solar system, or the swirling material being torn off Cygnus X1's companion star. Now layer the scale up by a factor of 1 trillion, and apply the same flattening to material spanning not millions of miles, but tens of thousands of light years, and you get the shape of a galaxy. Saturn's rings make the point almost absurdly well. They stretch across 175,000 miles, wide enough to fit 6 Earths side by side end to end, and yet in places they are barely 30 feet thick, a sheet of ice and rock so flat that scaled down to the width of a football field, it would be thinner than a sheet of paper. That is what conserved spin does to falling matter, given enough time to settle. Not a fluffy cloud, not a ball, but something closer to a record spinning on a turntable. In 2014, astronomers pointed a network of radio dishes in Chile at a young star still wrapped in its birth material, called HL Tauri, and captured the first clear image of a planet-forming disk in the act of organizing itself. Concentric rings, gaps swept clean by unseen forming planets, the whole structure looking uncannily like a diagram from a textbook, except it was a real photograph of a real system 450 light-years away, doing exactly what the ledger says it should. There's a reason the disk, once it forms, holds its shape and its orientation for millions of years rather than wobbling apart. The same spin that flattened it also stiffens it. The way a thrown discus holds its flat, level plane far more stubbornly in the air than a discus that left the hand without any spin at all. A rotating disc resists being tipped over. The rotation itself becomes a kind of structural memory, keeping the plane pointed in the same direction long after whatever set it's spinning is gone. Your entire solar system still orbits, roughly, in the same flat plane it first collapsed into. It has had 4.5 billion years to forget that orientation. It hasn't. This is where those numbers stop being separate facts and start looking like the same fact, photographed at different distances. In the 1970s, an astronomer named Vera Rubin pointed her instruments at the edges of spiral galaxies and measured something that shouldn't have been possible. Rubin had already spent 2 decades being told, one way or another, that she was in the wrong place. Princeton's graduate program wouldn't send her its astronomy course catalogue because it didn't accept women. When she first arranged to observe at Palomar Observatory in the 1960s, the building had no women's restroom, so she taped a paper skirt to the men's room door and used it anyway. She kept measuring. Nobody's discomfort with her presence changed what the telescope showed her. By every calculation available at the time, stars at a galaxy's outer edge, far from the dense, bright core, should orbit slowly, the same way Neptune drifts around the Sun far more sluggishly than Mercury does. Gravity weakens with distance. Orbital speed should weaken with it. It didn't. Rubin found that stars at the edges of the galaxies she studied were moving almost as fast as stars near the core, fast enough that, if the only gravity present were the gravity of the visible stars and gas she could see, those outer stars should have been flung off entirely, the whole galaxy unraveling within a single rotation. It hasn't unraveled. It hasn't been unraveling for over 10 billion years. Here's the part that took decades to sit with. The only way to explain a galaxy spinning that fast without tearing itself apart is if there's far more mass present than anything visible accounts for. 5 to 6 times more, wrapped in a halo far larger than the visible disk, gravitating but emitting no light of its own. Rubin's rotation curves became one of the strongest pieces of evidence that most of the mass in this universe isn't the kind that shines. We call it dark matter, and that name is mostly an admission. We know it holds the spin together. We do not know what it is. You are, at this moment, sitting inside a galaxy that should not be able to hold its own shape by the numbers we can directly see. And yet it does, night after night, because of something we've measured the gravity of and never once observed. Physicists have spent 40 years hunting for what that something actually is, and the hunt has mostly produced a long list of things it isn't. Detectors sitting beneath a mile of solid rock, shielded from the cosmic noise raining down constantly at the surface, have waited years at a time for a single dark matter particle to bump into ordinary matter and leave a trace. The candidates all have names: WIMPs, axions, sterile neutrinos, and, one after another, the most promising ones keep failing to show up where the equipment says they should be. The gravity is undeniable. The particle, if it is a particle at all, has yet to leave a fingerprint anyone can hold. Rubin herself, decades later, said that she'd rather be remembered for a question than an answer. She got her wish. Every spiral galaxy in the sky is still asking it, including the one you happen to be living inside. Rotation curves aren't even the only evidence anymore. In 2006, astronomers studying a distant collision between 2 enormous galaxy clusters, a system nicknamed the Bullet Cluster, found something that closed off most of the remaining alternative explanations at once. When the clusters collided, the visible gas in each one, which makes up most of their ordinary matter, slammed together and slowed down, dragged back by the collision the way 2 crashing cars crumple and stop. But gravitational lensing maps built from how the collision bent the light of galaxies far behind it, showed that most of each cluster's mass had sailed straight through the impact, barely slowed at all. Now sitting well ahead of the visible gas, it should have been traveling alongside. Something in each cluster was gravitating like matter and colliding like nothing at all. But the mechanism explaining any single object's spin, the falling, the flattening, the conserved rotation, was never the hardest question here. Here's the question that keeps physicists awake at night. Why, across galaxies separated by hundreds of millions of light years, with no way to have ever communicated or influenced each other, does the direction of that spin refuse to be random? Before we go there, sit with a smaller and stranger fact, because the same word, spin, is about to stop meaning what you assumed it meant. Physicists in the 1920s discovered that electrons carry a property they named, almost by accident, spin. It behaves mathematically like rotation. It produces a magnetic field, exactly the way a spinning charged ball would. So, naturally, physicists first pictured it as a tiny sphere, actually turning on an axis, not because the math was uncertain, but because where it led was uncomfortable. That picture had to be abandoned. If an electron were truly a small sphere spinning fast enough to produce the magnetic field it measurably has, the surface of that sphere would need to move many times faster than light, physically impossible under everything else we know to be true, and electrons, as far as every experiment ever run can tell, aren't spheres at all. They appear to be points, with no size, no surface, nothing that could be turning. The particles making up every atom in your body carry a property that behaves exactly like spin, produces the effects of spin, is even measured in the same units as spin, and, as best anyone has ever determined, isn't spinning at all, in any sense that would make sense to a person watching a top on a table. The proof came a few years earlier, almost by accident. In 1922, two physicists named Stern and Gerlach fired a beam of silver atoms through an uneven magnetic field, expecting the atoms to spread out into a smooth smear on the detector plate behind it, the way any ordinary spinning object, tilted at every possible angle, should scatter across a continuous range. Instead, the beam split cleanly into exactly two spots, nothing in between. Whatever property was steering those atoms didn't come in a smooth range of angles. It came in exactly two settings, like a switch rather than a dial. Nature, without warning anyone in advance, had just revealed that spin was quantized, sold in only two flavors, take it or leave it. Two young physicists, Uhlenbeck and Goudsmit, proposed the explanation in 1925, and even they tried to withdraw the paper before it was published. Embarrassed by how strange it sounded, it was already too late. Their supervisor had sent it in without telling them. The strangeness turned out to be real, and it turned out to be useful in a way neither of them could have guessed. Every time you or someone you love has ever lain still inside an MRI machine, the image on the screen was built entirely from this same property. The quantum spin of hydrogen nuclei in your own body's water, tipped and measured by a magnetic field, without a single one of those particles physically turning at all. We are not going to resolve that for you tonight. Nobody has. Quantum spin remains one of those places where the universe hands us a word borrowed from ordinary experience, lets us use it for a century of enormously successful physics, and never quite tells us whether the word means anything at the scale where it started. Now we can return to the promise from the start of tonight, the one about the Sloan survey, because this is where the mechanism we've spent the last half hour building stops being enough. Zoom out far enough, past individual galaxies, past clusters of galaxies, and the universe stops looking scattered and starts looking woven. Matter isn't spread evenly through space. It gathers into a vast lattice cosmologists call the cosmic web, long filaments of galaxies stretching for hundreds of millions of light years, connecting dense clusters at their intersections, with enormous, nearly empty voids stretching between the threads. It is, at the largest scale anyone has ever mapped, less like a scattering of dust and more like the structure of a sponge or a spiderweb built at a scale that makes a galaxy look like a single bead of dew, and your own galaxy is one bead among that entire woven structure. Sitting somewhere along one of its threads, two galaxies on opposite ends of one of those filaments, separated by hundreds of millions of light-years, have never exchanged a photon in a time frame that would let one influence the other's formation. Nothing about the physics we've covered tonight predicts that their spins should have anything to do with each other. Angular momentum conservation is a local rule. It governs a single collapsing cloud, a single galaxy, a single system. It says nothing about galaxy A caring which way galaxy B turns. And yet, when researchers using data from the Sloan Digital Sky Survey mapped the spin directions of tens of thousands of galaxies against the cosmic web of filaments connecting them, they found something that a purely random universe should never produce: a measurable bias. Galaxies near a filament tend to spin with their rotation axis aligned to that filament far more often than chance alone would allow. Not by a small margin easy to wave away as noise. Not in one isolated survey, either. Versions of this pattern have now turned up in more than one independent dataset, examined by more than one independent team. So now we have the first piece. Individual objects spin because they conserve rotation while falling. But this is a second independent piece of evidence, and it doesn't come from any single object at all. It comes from the relationship between objects that were never supposed to have one. Here's what almost nobody outside the field realizes. Astronomers don't actually agree on why this alignment happens, and the honest explanations on offer are stranger than a clean answer would be. One possibility is almost mundane. Galaxies don't form randomly, in isolation. They condense out of gas already flowing along vast filamentary structures, the largest architecture in the universe, built from the way matter clumped together in the first place. Cosmologists call this idea tidal torque theory. Neighboring clumps of early matter tug on each other unevenly as they grow, and that uneven tugging can imprint a shared directional bias before a single star has ever ignited. If the raw material feeding a galaxy's growth is already moving along a filament's direction, some of that directional bias could get inherited into the galaxy's spin, the same way Earth inherited its solar system's leftover rotation. Under this view, the alignment isn't magic, it's angular momentum conservation again, just operating on a scale 100,000 times larger than anything we've discussed so far. The same accounting trick, applied to the largest structures that exist, but here's what those explanations don't fully cover. The strength, and even the direction of the alignment appears to shift, depending on a galaxy's mass, its shape, and how close it sits to the filament's core. Details that a single clean mechanism should not produce, and that current simulations still struggle to reproduce in full. Some studies find spins aligned parallel to their filament. Others, at different mass ranges, find spins tilted perpendicular instead. Nobody currently in this field claims to have the complete explanation. Here is the tension this documentary is not going to resolve for you, because nobody has resolved it for themselves yet either. Either this alignment is angular momentum patiently obeying the exact same law we've traced tonight, from a single falling dust cloud all the way up to the largest structures that exist, meaning the universe is, at every scale, keeping one single accounting book with no exceptions. Or it is a seam in that explanation, a place where the tidiness runs out and something about the structure of the cosmos still needs a physics we haven't written yet. We are going to sit inside that question, the same way the universe itself seems to be sitting inside it. In 1949, on the occasion of Einstein's 70th birthday, a quiet, meticulous logician named Kurt Gödel gave him an unusual gift, a solution to Einstein's own equations of general relativity, describing an entire universe that rotates. Gödel and Einstein had walked together nearly every day for years at Princeton, an unlikely friendship between the physicist who reshaped the universe and the mathematician who had, a decade earlier, proven that any sufficiently powerful system of logic must contain truths it cannot prove from within itself. Gödel turned that same instinct. Find what a system permits, whether or not the system's inventor intended it, onto Einstein's field equations, and found something Einstein had never anticipated. If the universe were filled with rotating matter arranged just so, space-time itself would spin around a preferred axis. Time and space would tangle together in a way that made it mathematically possible, in principle, to travel into your own past. Picture ordinary time as a road. You can only travel forward along it, and every mile marker you pass falls permanently behind you. In a Gödel universe, thanks to the dragging effect of all that rotating matter, the road eventually curves back on itself. Not metaphorically, but in the actual geometry of space-time, so that travelling forward for long enough and far enough could in principle return a traveller to a moment already lived, not a memory of the past itself, waiting to be walked into a second time. Einstein's response was measured and a little uneasy. He acknowledged the mathematics was valid and admitted the result will be a considerable subject of study. He also seemed relieved that the actual universe we observe doesn't look like Gödel's. No large-scale rotation has ever been directly measured, no closed time-like loops, nothing letting cause chase its own effect backward. Not because the math was wrong, because nobody has ever found the universe actually arranged that way. But nobody has ever found it, and it has been ruled out, are two very different sentences. And the gap between them is exactly where the next uncomfortable question lives. If the universe rotated the way Gödel's mathematics allowed, there should be a trace of it left over from the earliest light we can see. The cosmic microwave background, the faint afterglow of the universe when it was 380,000 years old. In the early 2000s, a NASA satellite called WMAP mapped that afterglow's finest details for the first time. And cosmologists studying the results noticed something odd sitting in the data. Patterns in the largest scale temperature variations that seem to line up with an axis running roughly through our own solar system. Rather than pointing in some direction with no relationship to us at all, researchers, only half joking, started calling it the axis of evil because a universe that shouldn't prefer any direction over another appeared, faintly, to prefer one. Let that arrive slowly. This alignment, if it's real and not a statistical accident or an artifact of how the measurement was taken, would be one of the strangest findings in modern cosmology. A universe with the barest whisper of a preferred axis, embedded in light that has been travelling toward us for over 13 billion years. Most cosmologists suspect it's a coincidence, a trick of limited data and the small number of large-scale patches available to measure, rather than an actual rotation of everything. And yet a second, far more precise satellite called Planck, launched a full decade after WMAP with better instruments and no shared design flaws to blame, looked again in the 2010 seconds, and found the same faint alignment sitting in the same place. The signal is faint enough, and appears in few enough independent measurements, that nobody treats it as confirmed. But it hasn't vanished either. Through two entirely different missions built years apart, run by separate teams, using separate hardware. Nearly 2 decades after it was first noticed, it is still sitting in the data, unresolved, neither confirmed as real nor dismissed as noise. And tonight, that's where we're going to leave it. Now hold everything you've heard so far tonight. The falling, the flattening, the conserving, and watch it happen once, from beginning to end, to a single star. In November 2014, a robotic survey scanning the sky for anything that suddenly brightens caught a galaxy 290 million light-years away, doing something it hadn't been doing the week before. A star, wandering too close to the supermassive black hole at that galaxy's center, crosses an invisible boundary. The black hole's gravity is stronger on the near side of the star than the far side. Not by a little, by enough to matter. the star begins to stretch. Meanwhile, the stretching accelerates. What was a sphere becomes a teardrop, then a thread, then a stream of gas tens of thousands of miles long, still glowing with the star's own leftover heat. Half of that stream escapes outward, flung away and lost to interstellar space forever. The other half, carrying the star's own leftover spin, has nowhere to go but down into a disk. Meanwhile, that disk begins organizing itself in real time, exactly the way a stellar nursery does, exactly the way Saturn's rings do, falling, flattening, speeding up as it tightens, all in the span of weeks instead of millennia. Temperatures climb past 1,000,000 degrees. X-rays begin pouring out of a region no larger than our solar system. Meanwhile, 5 years after the event was first spotted, astronomers studying the X-ray data noticed something buried in the flickering brightness. A rhythm, repeating every 131 seconds, on and off, with a regularity too clean to be random noise. Something in that disk was completing a cycle at almost exactly the same interval, over and over, thousands of times. The likeliest explanation, published in the journal Science, is the strangest part of the whole event. A clump of debris caught in an orbit right at the very edge of the black hole. The last orbit before falling in becomes unavoidable, circling once every 131 seconds. And the size of that innermost edge depends on one thing above all else: how fast the black hole itself is spinning. A slower black hole pushes that last safe orbit farther out, a longer rhythm. A faster one drags it in tight, a quicker one. The flicker in the X-rays wasn't just noise from a dying star, it was the black hole's own spin, signing its name on the wreckage. A star that had existed for hundreds of millions of years was gone within a season. What it left behind, entirely by accident, was a stopwatch reading on a black hole nobody had measured the rotation of before. Destruction, it turns out, is one of the most reliable ways this universe has of confessing how fast something was spinning. Not because it wants to be measured, because spin doesn't know how to hide from an ending violent enough to expose it. Not every measurement of spin needs a dying star, though. Some of the strangest evidence has been sitting in something far gentler, far closer to home than any of this, and far more commonly misunderstood. Closer, in fact, than you might expect. Here's a piece of trivia almost everyone has heard, and almost everyone has heard wrong: that water drains clockwise in one hemisphere and counterclockwise in the other because of the Earth's rotation. It's not true, at least not at the scale of a sink or a bathtub. The rotating Earth does produce a genuine deflecting effect, called the Coriolis force, that curves the path of anything moving across large distances. It's the reason hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern, the reason long-range artillery shells in the First World War landed slightly off target until gunners corrected for it. But that force is proportional to how large and how slow the moving system is. A hurricane spans hundreds of miles and churns for days. A bathtub drains in under a minute, across a basin barely large enough to sit in. At that size, the Coriolis effect is real, but almost immeasurably faint, thousands of times weaker than the influence of whatever small asymmetry already exists in the tub's shape, or however you happen to be sitting in it 5 minutes before you pulled the plug. In 1962, an engineer named Asher Shapiro at MIT proved the point could still be demonstrated, if you were patient enough to do it properly. He built a perfectly symmetrical tank 6 feet across, let the water sit completely undisturbed for a full day so every trace of leftover motion could settle, and only then, without touching it, opened a small drain at the center. Under those exact conditions, and only under those exact conditions, the water reliably spiraled counterclockwise, the direction the genuine, if tiny, Coriolis force predicted for the Northern Hemisphere. A team in Sydney repeated the experiment a few years later, with the same patients, and got the mirror image, clockwise. as their own hemisphere's physics demanded. The lesson isn't that the myth is completely wrong. It's that the planet's rotation is genuinely, measurably reaching into everything on its surface, including the water in your sink, and almost every single time you've ever pulled a drain plug. That whisper-quiet influence lost to something as small and as ordinary as the last time you stirred the water with your hand. There's something almost comforting in that mismatch of scale. The same force capable of steering a hurricane 1,000 miles across is, in your bathroom sink, so faint it can be beaten by a light touch of your fingertip. You've been overpowering a planetary scale force your entire life without ever knowing you were doing it. Every single time you've washed your hands. Scale, it turns out, is the quiet decision maker behind almost everything in tonight's story. The same rotation that is far too weak to steer a sink is exactly strong enough, applied to an ocean instead of a basin, to steer entire currents circling whole ocean basins for centuries. Nothing about the underlying force changed between the two. Only the size of the thing it was allowed to act on. Your own body carries a spinning system every bit as easy to fool. Somewhere behind each of your ears, sealed inside bone, sits a set of 3 fluid-filled loops, oriented in 3 different planes, doing one job every second of your life, telling your brain which way you're turning. When your head rotates, the bone around those loops turns with it almost instantly. The fluid inside, though, has weight and resists the change. Inertia holds it back for a fraction of a second, and that lag, that tiny relative sloshing, bends a cluster of hair-thin sensors at the base of each loop. Bend them one way. Your brain reads turning left. Bend them the other, turning right. It's an internal gyroscope built from nothing more than a few drops of fluid and the same physics that made a dust cloud spin 4.5 billion years ago. Here's where it gets stranger. Spin your whole body around several times, then stop abruptly, and the fluid in those loops doesn't stop with you. It keeps drifting for a few extra seconds, coasting on its own momentum, still bending the same sensors, still insisting to your brain that you are turning, even though every other part of you, and the room around you, has gone completely still. Your eyes will often flick involuntarily in short, rhythmic jerks during those seconds, chasing a rotation that only your inner ear still believes is happening. That is the entire mechanism behind the dizziness of stepping off a playground roundabout, or standing up too fast, or the spinning room sensation some people feel in the last seconds before sleep takes them. Not a malfunction, but conserved momentum, playing out in a few drops of fluid instead of a solar system. Nothing about that fluid asked to keep moving after you stopped. It simply hadn't been given a reason to stop yet. The exact same debt every rotating object in this documentary has been paying tonight, collected in the smallest structure inside your own skull. Astronauts returning from long stretches without gravity report a version of this that can last for days rather than seconds, their inner ear fluid having silently recalibrated itself to an environment with no reliable down, leaving them dizzy on solid ground until the system relearns what stillness is supposed to feel like. The sensation of spinning, it turns out, is never really about whether you're spinning. It's about whether the fluid in your skull and the world in front of your eyes currently agree. This is one of the strange places where the smallest scale in tonight's story and the largest one fold back on each other. A dying star's collapse and the fluid inside your skull are obeying identical rules, one measured in millions of miles, the other in millimeters. And both of them, tonight, are quietly doing it while you lie still, listening, on the edge of sleep. Even the part of you responsible for knowing which way is up has never fully escaped the pull of everything we've covered so far tonight. Zoom out from the inner ear to the largest orbit your body is currently completing, and the numbers stop being personal and start being geological. The sun, carrying Earth and everything on it, takes roughly 230 million years to complete a single orbit around the center of the Milky Way. Astronomers sometimes call this one galactic year. And by that calendar, the solar system is only about 20 of them old. 20 laps, completed since the Sun and its planets first condensed out of that collapsing cloud. Now, place a single human lifetime on that calendar. The last time our solar system was in roughly this same position, on this same stretch of its galactic orbit, was close to 230 million years ago, a period when the first true dinosaurs were just beginning to appear, when the supercontinent Pangaea hadn't yet finished pulling apart, when nothing resembling a flower had ever bloomed anywhere on the only planet we know to have them. Everything you have ever personally known, every war, every civilization, every human being who has ever lived, fits inside considerably less than 1/100th of a single one of these laps. You are riding a wheel large enough that dinosaurs never lived to see it turn even once. The orbit itself isn't even a flat, simple circle. As the solar system loops around the galactic center, it also drifts gently up and down through the galaxy's disk, crossing the crowded midplane roughly every 30 million years or so, before drifting back out the other side, like a horse on a carousel that also happens to be bobbing. Some researchers have noticed that mass extinctions in the fossil record seem to loosely cluster on a similar rhythm, and have proposed that each crossing might stir up comets from the outer solar system or expose Earth more directly to cosmic radiation. It remains a contested hypothesis, argued over for decades without a clean resolution. The correlation is there in the data, faint and stubborn, and nobody has proven whether it's cause, coincidence, or an artifact of how the fossil record itself was preserved. Even if that particular rhythm turns out to be noise, the larger orbit is not in question. Every extinction, every ice age, every empire that has ever risen and collapsed on this planet happened within a single, unremarkable bob up and down through the galactic disk. One small wobble in a lap that won't complete for another 200 million years. Hold that for a moment. Time, somewhere on the far side of this current lap. Whatever comes after us, if anything does, we'll be looking back at tonight the same way we look back at the first dinosaurs. A marker passed once, on a wheel too large for any one species to ever see turn all the way around, in either direction, at any point in its existence. No civilization that has ever risen on this planet has lived to see even 1% of a single galactic year complete. Every one of them, without exception, arrived, spun for a moment, and vanished within the same tiny arc of this current, unhurried lap. There is a question hiding underneath everything you've heard tonight, and it's simpler than the physics and harder than any of it. Spinning, compared to what? In 1689, Isaac Newton described a simple experiment. Hang a bucket of water from a twisted rope and let it spin. At first, the bucket turns, but the water inside stays still, its surface flat. The water hasn't caught up yet. Then friction drags the water into the same spin as the bucket, and its surface curves upward at the edges, climbing the sides in a shallow bowl shape. Newton's question was this: what is the water spinning relative to, at the exact moment its surface curves? Not the bucket. The water and the bucket are turning together by then, with no relative motion between them at all. Newton's answer was startling for its time. The water was rotating relative to space itself, an absolute, fixed backdrop that exists whether or not any matter is around to measure against it. 2 centuries later, a physicist named Ernst Mach pushed back hard. There's no way, he argued, to ever detect absolute space directly. Every rotation we have ever measured, including the buckets, has only ever been measured relative to something else that exists. The walls of the room, the earth, the distant stars scattered across the sky. Take away every other object in the universe, leave only the bucket and the water and nothing else anywhere. And Mach insisted the entire question would become meaningless. Spinning relative to what, if there's nothing left to spin relative to? Nobody has ever been able to run that experiment. Obviously, you cannot empty the universe to check, but the ghost of Mach's question is exactly why does the universe itself rotate is such a genuinely strange thing to ask. Every other kind of spin we've discussed tonight, Earth, the Sun, a galaxy, a black hole, makes sense because there's a larger frame of reference to spin relative to. The universe, by definition, has nothing outside itself to spin against. If it is rotating, it may be rotating relative to nothing at all, a kind of motion with no witness, on any scale, except the motion itself. Einstein took Mach's challenge seriously enough to try building it directly into general relativity and the frame dragging we covered earlier tonight. The Earth twisting space around itself, a black hole forcing its ergosphere to turn, is part of what came out of that attempt. Rotating mass really does drag the local structure of space along with it, exactly as Mach's intuition demanded. But general relativity never fully closed the loop the way Mach wanted. In Einstein's finished equations, space-time itself still behaves, in certain respects, like a fixed backdrop that can carry its own rotation independent of any matter at all, which is precisely how Gödel found room, decades later, to construct an entire universe that spins with nothing external for it to spin against. Newton's bucket, spinning quietly in a room in 1689, turned out to be asking a question that outlived him by 3 centuries and still isn't fully settled. The same question, in a smaller form, you just asked yourself a moment ago without realizing it. Now add one more layer and follow the debt all the way back to its very first payment. We've spent tonight tracing spin backward, a galaxy's rotation to a filament's flow, a filament's flow to the clumping of early matter, a star's rotation to a collapsing cloud, a cloud's rotation to a residual drift too small to measure. But that residual drift itself had to come from somewhere. Follow it back far enough, past every cloud, past every galaxy, past the first stars, and the trail ends less than 1 second after the Big Bang, in a period called inflation, when the universe expanded from smaller than an atom to astronomical size in a fraction of an instant. Here's what almost nobody completely misunderstands about that period. It wasn't smooth. Quantum mechanics guarantees that even in a near-perfect vacuum, tiny fluctuations flicker in and out of existence at every point in space, too small and too brief to matter under ordinary conditions. Inflation caught those fluctuations mid-flicker and stretched them instantly into structure spanning the entire observable universe. The same tiny quantum static that would later decide where galaxies clump, where filaments form, and which way the earliest collapsing gas would already be leaning before gravity ever got involved. This is as far back as the trail goes, and it doesn't end in an answer. It ends in a fog of quantum uncertainty from the universe's first fraction of a second, a period we can model with extraordinary precision in aggregate and can never, even in principle, know in exact detail, because the fluctuations that seeded it were random by the deepest laws of physics we have. Not merely unmeasured. The spin under your feet tonight, the spin in the star warming your skin, the spin of the galaxy holding both, may ultimately trace back to a coin flip made by the universe itself at an instant so early that instant barely means anything yet. Nothing has to spin, and yet nothing, once it learned how, has ever fully agreed to stop. Not since a moment so early there was no before to compare it to. We are not going to pretend that's a satisfying place to end the chain. It isn't. It's simply where the chain runs out. Here's what makes it stranger rather than simpler. Those same quantum fluctuations have been measured, indirectly, in the cosmic microwave background, the same afterglow that may or may not be hiding a whisper of rotation in its largest patterns. The tiny temperature variations across that ancient light match, in exhaustive statistical detail, the predicted signature of inflation stretching quantum noise across the sky. We can read the general texture of that first instant with remarkable confidence. We simply cannot, even in principle, rewind the tape and ask why the noise fell the particular way it fell, rather than some other way that would have left the universe looking entirely different. or spinning some other direction, or perhaps not spinning at all. In September 2015, a detector in Louisiana and another in Washington state, 3,000 kilometers away, both flinched at the exact same instant, in a way neither had ever flinched before. A signal you could, in principle, have felt too if your body were a sensitive enough instrument. The two facilities, built to detect a distortion in space smaller than 1/10,000th the width of a proton, had been listening for gravitational waves for years without hearing anything. An engineer named Rainer Weiss had first sketched the concept for a detector like this back in 1972 on a blackboard for a class, a design he assumed at the time was more of a teaching exercise than a blueprint anyone would actually fund. It took over 4 decades and hundreds of scientists before that sketch became a real machine, sensitive enough to hear what it was built for. What it heard that September was the last fraction of a second of 2 black holes spiraling into each other, roughly 1 billion light-years away, each one tens of times the mass of the Sun, orbiting closer and closer, spinning faster and faster as they fell toward a collision. The same conserved rotation we've traced all night, amplifying one final time as the distance between them collapsed to nothing. In the last 20 milliseconds before they merged, they had accelerated to more than half the speed of light, spinning around their shared center faster than any object in this documentary so far. Then, briefly, more power was radiated away as gravitational waves in that final instant than every star in the observable universe combined was producing invisible light, all at once. The 2 black holes merged into one, slightly lighter than the sum of their 2 starting masses. The missing mass converted entirely into the ripple that crossed 1 billion light-years of empty space and arrived at 2 detectors on Earth within a few thousandths of a second of each other. Even the newborn black hole left behind carries a memory of all that violence. Its own spin, inherited and reshuffled from the 2 spins that fell into it, still turning, still obeying the same debt every object in this story has owed since the moment it first began to fall. Weiss shared the Nobel Prize for this discovery in 2017, alongside Kip Thorne, the same physicist who, decades earlier, had bet Stephen Hawking that Cygnus X1 really did contain a black hole. Thorne spent one career arguing that these objects existed from indirect evidence alone, and eventually helped build the very machine that let humanity, for the first time in its existence, actually hear 2 of them collide. More than 100 similar mergers have been detected since that first one in 2015. Each one a fresh accounting of spin, gained and lost and radiated away, arriving from galaxies most of us will never see with our own eyes, in a language that had been reaching Earth for 1 billion years before anyone finally built an ear patient enough to hear it clearly and confident enough in the physics to trust what it heard. Everything you've heard so far tonight has followed the same pattern. Matter falls, spin conserves, rotation speeds up, but 2 of our own neighboring planets prove that the pattern can be interrupted. And the way it breaks is almost as informative as the rule itself. Mercury, closest to the Sun, was assumed for decades to be tidally locked entirely. One face permanently baking in sunlight and the other frozen in permanent night, the same way our moon shows Earth only one face. Radar observations in 1965 proved that assumption wrong. Mercury isn't locked 1-to-1 at all. For every 2 trips it makes around the Sun, it turns on its axis exactly 3 times. A precise, stable ratio, locked in place by the Sun's tidal pull acting on Mercury's slightly elongated shape. But not the simple lock everyone had expected. Stand on Mercury's surface at certain longitudes, and you'd watch the Sun rise, pause, briefly reverse course, and set again before finishing a single Mercury day. Venus went further off script entirely. It rotates backward compared to almost every other planet, and it does so with a staggering lack of urgency. A single rotation takes 243 Earth days, longer than the 225 days it takes Venus to orbit the Sun completely. A Venusian day is longer than a Venusian year. Nobody has a fully settled explanation for why its spin ended up backward and this slow. Leading theories point to a thick, sluggish atmosphere dragging on the solid planet beneath it over billions of years, gradually stealing rotation the way Earth's moon steals ours, but in ordinary daylight rather than tides. Not gently slowed, reversed entirely, and left to crawl. Spin, it turns out, is not a promise every world keeps in the same way. Some worlds fall neatly into the ledger we've traced tonight. Others fight it for billions of years and end up somewhere stranger than anyone predicted. Most moons in this solar system have already reached the quiet end of that fight. Our own moon, and nearly every large moon orbiting Jupiter and Saturn, have long since been locked by their planet's gravity into showing only one face, their rotation and orbit brought into perfect agreement over billions of patient years. Mercury and Venus are, in their own ways, still mid-argument. Mercury settled into an unusual but stable compromise. Venus still grinding, slowly and backward, toward whatever equilibrium waits for it, tens of millions of years down the road, if anything ever waits for it at all. The same tidal mechanism, applied to different starting conditions, produces a moon that surrenders cleanly and a planet that fights for eons and loses anyway, just slower and stranger than everything around it. Nothing about the underlying law changed between the two outcomes. Only the mass, the distance, and the amount of time already spent arguing. The same three variables, in different proportions, deciding every outcome in tonight's entire story. Change any one of the three, even slightly, and Venus could just as easily have ended up locked as neatly as our own moon. Its long, backward day never happening at all. Not everything manages a smooth single-axis rotation, the kind you've been hearing about most of tonight. Some objects tumble instead, and one comet has shown us exactly what that looks like up close. In 2014, a European spacecraft called Rosetta arrived at a comet called 67P, shaped like a rubber duck rather than any tidy sphere, and settled into orbit around it for 2 years. The first mission in history to accompany a comet at close range, rather than simply flying past. What Rosetta found wasn't a body spinning cleanly around one fixed axis, the way a planet does. It was tumbling, its rotation slowly drifting in direction over time. The axis itself wandering, made worse by jets of gas and dust erupting unevenly from its surface as sunlight warmed the ice beneath. Every outburst nudged the spin a little further off whatever axis it had settled on before. An object without enough mass to pull itself into a sphere, and without anything smoothing out its rotation, simply keeps the chaotic tumble it was born with, perturbed further by its own outgassing every time it nears the Sunday. There is no ledger correcting it back onto a clean, stable spin. Some things in this universe never get the chance to settle at all. Rosetta's own lander, a small probe called Philae, found this out the hard way. It touched down on 67P's surface in 2014, bounced twice off the low, uneven gravity, and came to rest wedged in a shadowed crack where sunlight rarely reached its solar panels. Silenced within days, awakened briefly months later as the comet's changing distance from the sun shifted the angle of light, then lost again for good. A machine built with exacting precision on Earth met a world that had never agreed to hold still or spin predictably. For anyone, the mission team back on Earth had planned Philae's landing, assuming a far gentler, more orderly rotation than the comet actually turned out to have, and the harpoons designed to anchor the lander to the surface on touchdown failed to fire at all. One small mismatch between the tidy spin engineers expected and the tumbling one that was actually waiting, compounding into a mission that gathered only a fraction of the data it was built for. Rosetta itself, orbiting patiently overhead for 2 more years after Philae went quiet, kept measuring that same chaotic tumble in detail nobody could have planned around in advance, cataloguing an object that had simply never been given the chance, in 4.5 billion years, to settle into anything as calm as the planets and moons you've spent most of tonight hearing about, and likely never will. Every close pass by the sun adds a fresh burst of chaos before the last one has finished settling, keeping the comet permanently a step behind whatever stable spin it might otherwise have found. Not every rotation in tonight's story has been this orderly. Most of what we've covered has been the exception that got to calm down. This is what spin looks like before something forces it to behave. Remember the pulsars you heard about earlier tonight? The collapsed cores flashing a beam of radio waves, with every single rotation regular enough to be briefly mistaken for an alien signal. It turns out their regularity is useful for something far stranger than telling you the time. A pulsar's spin is so stable that its radio flashes arrive on Earth with a predictability rivaling the best atomic clocks ever built, drifting, if at all, by only a few millionths of a second over years of continuous monitoring. In 2023, an international collaboration of radio astronomers announced they had spent 15 years timing dozens of these pulsars scattered across the galaxy, watching for the tiniest irregularities in their otherwise flawless rhythm. What they found was a faint, shared stretching and squeezing pattern across all of them at once. Evidence, they argued, of gravitational waves so long that a single wave crest can take years to pass. Generated not by one dramatic merger like the one we covered earlier, but by countless pairs of colossal black holes throughout the universe's history, orbiting each other slowly across cosmic time. Here's what makes the method itself remarkable. Nobody built this detector. It was already sitting in the sky, assembled by dying stars that collapsed for entirely unrelated reasons, billions of years before any astronomer thought to time them. The universe accidentally built its own gravitational wave observatory out of leftover stellar corpses, and it took us decades to notice we could read it. Consider what that actually required. Dozens of pulsars, scattered across thousands of light years from each other and from Earth, each one spinning with its own private, near-perfect rhythm, had to be monitored simultaneously for a decade and a half before a signal this faint could be teased out of the noise. No single pulsar showed anything unusual on its own, only by comparing all of them at once, watching for a shared, correlated stretching that rippled through the whole array in the same pattern gravitational waves predict, did the signal become visible at all. It is, in a very real sense, a portrait of the universe's rotation and orbital history painted using the most reliable clocks nature has ever assembled. Clocks built entirely by accident, out of the same collapsing cores we met earlier tonight, spinning hundreds of times a second. Somewhere in that faint, galaxy-wide hum are the echoes of countless black hole pairs we will never observe directly, each pair carrying its own conserved spin toward a merger that may not finish for millions of years yet. The instrument reading their signal wasn't built by any one civilization's ambition. It was built by death, scattered across the galaxy and simply left running, long before anyone existed who would one day need it or know to go looking for it at all. Every dying star that becomes one of these pulsars adds one more instrument to an array. None of them were ever consulted about joining, tuning itself a little more precisely with every additional year of data. Everything you've heard so far tonight has been about matter falling into rotation it can't shed. Now consider the opposite problem. An instrument that has to fight rotation every second of its life just to hold perfectly still, so that you can eventually see the picture it took. A space telescope like Hubble, or the James Webb Space Telescope drifting nearly 1 million miles from Earth, has no ground to brace against and no air to resist it. Left alone, the faintest disturbance. A solar photon pressing unevenly on one side of its sunshield, a fuel line venting a whisper of gas, would be enough to set the entire spacecraft slowly tumbling, ruining any image that needs minutes or hours of exposure to gather enough faint, ancient light. To stay locked on a single distant galaxy for that long The telescope doesn't fire thrusters, which would shake it. Instead, it carries several heavy wheels spinning inside its own body, called reaction wheels, and speeds one up or slows another down by fractions of a rotation whenever the spacecraft needs to turn. Here's the part that connects it to everything we've covered tonight. Because angular momentum has to stay conserved for the telescope and its wheels together, spinning a wheel, one direction forces the spacecraft's body to twist very slightly the other way. The exact same ledger a dust cloud or a neutron star obeys, borrowed deliberately, on purpose, by engineers who needed a spacecraft to hold impossibly still. The telescope doesn't fight rotation by refusing to spin. It fights rotation by spinning something else instead, constantly, invisibly, so that the instrument pointed at the sky never has to move at all. Every crisp, motionless image either of those telescopes has ever produced exists because something inside it, out of sight, never stopped quietly turning. Hubble carries 4 of these reaction wheels, spinning at thousands of rotations per minute, precisely because a spare is needed in case one fails, which one very nearly did in 1990, weeks after launch, forcing engineers to manage the telescope's pointing with only 3 fully trusted wheels until a servicing mission years later could replace the 4th. James Webb, built decades afterward and designed never to be serviced by astronauts at all, carries its own set, sized and balanced with even less margin for error, because there will never be a repair crew a million miles from Earth. There is something almost touching about the engineering choice underneath all of it. Rather than fight the universe's oldest rule about conserved rotation, the engineers who designed these telescopes simply borrowed it, aiming it inward instead of outward, so that the most distant, most ancient light these instruments have ever captured could arrive on a detector that never once had to tremble while gathering it. Hour after patient hour. Every deep field image either telescope has released to the public exists because a handful of spinning wheels, tucked out of sight, inside the spacecraft's body, did their job without a single person on the ground needing to think about it. Here's a version of spin's influence so subtle you'd never notice it without decades of careful measurement. An asteroid's own rotation can gradually steer where it ends up, decades or centuries later, using nothing but sunlight. An asteroid tumbling through space absorbs sunlight on whichever face happens to be pointed at the sun, warms slightly, and then re-radiates that heat back into space as the asteroid's own rotation carries the warmed face into shadow. Because the warmest point on the surface lags slightly behind the point directly facing the sunday, rotation doesn't let the heat escape from exactly where it landed. The escaping heat pushes back on the asteroid with a tiny, lopsided nudge, off-center just enough to very slowly raise or lower its orbit. Physicists named it the Yarkovsky effect, after the obscure Russian engineer who first proposed it around 1900, decades before anyone could measure anything so faint. The push from a single afternoon of sunlight is smaller than the weight of a few grains of sand, but applied continuously across millions of years, it has been measured shifting real asteroids by thousands of miles from where gravity alone would have placed them. Enough for objects that pass near Earth to matter for exactly the kind of prediction that keeps planetary defense scientists awake at night. 2 asteroids, identical in every way except the direction they happen to spin, will drift onto measurably different paths over enough time. One nudged gently inward, the other gently out. Spin decides more than shape here. Spin quietly decides destiny. One imperceptible photon at a time, for anything small enough not to fight back. NASA's own planetary defense teams now factor the Yarkovsky effect directly into their calculations for tracking near-Earth asteroids decades into the future, because ignoring it means the predicted position of a hazardous object can drift by a margin large enough to matter. One especially telling case involved an asteroid called Bennu, visited by a spacecraft called OSIRIS-REx specifically to measure its rotation composition, and surface temperature well enough to calculate the Yarkovsky push acting on it. The mission refined Bennu's predicted future path enough to substantially narrow the uncertainty around a very distant, very low probability, close approach with Earth over a century from now. Not by finding a new force nobody had considered, but by finally measuring precisely enough how one small, spinning rock relates to the sunlight falling on it. It is a strange thought for you to sit with tonight. Somewhere in a mission control room, engineers spend years refining exactly how fast and in which direction a boulder-sized world tumbles through space, because the direction it happens to spin, multiplied out across a century of quiet photon pressure, is the difference between a rock that stays comfortably out of the way and one that eventually doesn't. Nobody chose which way any given asteroid happened to spin. The consequences of that choice, made by nothing more than the leftover chaos of its own formation, are still being tallied today. Everything tonight has been rotation nobody asked for, inherited from a collapsing cloud or stolen slowly by a moon. Somewhere in the coming decades, humans may finally build something that has to spin deliberately, because nothing else will make it livable. Long stretches without gravity measurably weaken bone density and muscle, reshape fluid distribution in the body, and strain the heart in ways researchers are still fully cataloguing after decades of studying astronauts aboard the International Space Station. One of the oldest proposed solutions predates real spaceflight entirely. Build a station shaped like a wheel or a cylinder, spin it, and let the same outward-flinging force that flattened a collapsing cloud into a disc press against the inside of the hull instead, standing in for gravity that isn't otherwise there. Stand on the inner rim of a large enough spinning cylinder, and the physics pressing your feet down is, for every practical purpose, indistinguishable from the pull that has held you to Earth's surface every day of your life. The engineering is harder than the concept. Spin a habitat too small or too fast, and the difference in force between someone's head and someone's feet becomes noticeable and nauseating. The same inner ear confusion we felt spinning off a playground roundabout earlier tonight. Except this time, it never fully goes away. Get the radius large enough, and the spin needed to simulate a comfortable one, gravity becomes gentle enough that nobody inside would necessarily notice they were turning at all. If humans ever do build a home like that among the stars, it will be the first time in this entire story that something spins because we decided it should, rather than because it had no other choice. A physicist named Gerard O'Neill worked out much of the practical mathematics behind these designs in the 1970s, sketching cylinders miles long, spinning slowly enough that the people living along their inner surface would feel a comfortable approximation of Earth's own pull, farmland and rivers, an open sky curving gently upward on either side until they met overhead. None of it has been built. The engineering obstacles are not small. Assembling a structure that size, spinning it up without tearing itself apart, keeping its rotation axis stable over decades. But nothing about the physics itself is speculative. It is the same physics that flattened a collapsing cloud into the disk our own planets formed from, run in reverse and on purpose, by people who wanted the outward-flinging half of that story instead of the inward-falling half. Small versions of the idea have already flown. Some early crude spacecraft designs spun the entire capsule gently to simulate a fraction of gravity for their occupants, and engineers today still study spinning tethers and rotating segments as one of the more plausible, near-term answers to the health toll of long journeys to Mars. The oldest force in this documentary, the one that built solar systems and flattened black hole disks without being asked, may end up being the same one that finally lets humans live somewhere besides the surface of a single planet. Every rotating object you've heard about tonight has been either speeding up or holding steady. There is exactly one place in this story where spin finally, truly, runs out, and it takes longer than almost anything else in this universe to get there. In 1974, Stephen Hawking, the same physicist who once bet against his own life's work, showed that black holes aren't perfectly black after all. Quantum effects at the very edge of the event horizon let a faint trickle of particles escape over unimaginable stretches of time, carrying away a whisper of the black hole's mass and, with it, a matching whisper of its spin. The process is so slow for a stellar mass black hole that it would take far longer than the current age of the universe, many times over, just to lose the first measurable fraction of its rotation. For the largest supermassive black holes, sitting at the centers of galaxies, the timescale stretches even further, into numbers that stop feeling like time at all and start feeling like a different unit entirely. But the direction of travel is not in question. Every black hole in this universe, without exception, is radiating that whisper away right now, this instant. As you listen, Cygnus X1, spinning at more than 95% of its absolute limit. The same black hole whose existence Stephen Hawking once bet against, is losing that spin one impossibly faint particle at a time, and will keep losing it for a length of time that makes the 230 million years of a single galactic orbit look like the blink of an eye repeated a trillion times. Someday, unfathomably far in the future, long after every star has gone dark and every galaxy has drifted beyond the reach of every other, the last black holes will finish evaporating entirely. Spin and all, gone. The debt, finally, fully repaid. Nothing in this universe, it turns out, gets to keep its rotation forever. It only gets to keep it for longer than anything else does. Hawking arrived at this discovery almost by accident, trying to disprove a colleague's suggestion rather than confirm his own, and reportedly found the results so unsettling at first that he checked and rechecked the mathematics for months before accepting it. A black hole, the one object in this entire documentary that seemed built to keep everything it ever swallowed, including its own spin, forever, turned out to be leaking the whole time, at a rate so faint that not one photon of it has ever been directly detected by any instrument built so far. We trust the process is real because the mathematics connecting it to everything else we've covered tonight, gravity and quantum mechanics both, has held up every other time it's been tested. We have simply never lived long enough, and never will, to watch even the very first stage of it happen to completion. Every black hole in this documentary, without a single exception, is quietly running down a clock longer than the rest of the universe's entire future. Not every consequence of spin you've heard about tonight looks like violence or slow decay. Some of it looks, almost unaccountably, like geometry, a shape you could point to yourself if you knew exactly where to look. At Saturn's North Pole sits a six-sided jet stream, a hexagonal pattern in the clouds roughly twice the width of Earth, each side longer than our entire planet, that has held its shape since spacecraft first photographed it clearly in the 1980s, and shows no sign of drifting into a circle, the way ordinary fluid turbulence should. Laboratory experiments spinning tanks of fluid at different rates have managed to reproduce hexagons and other polygon shapes under the right conditions, suggesting the pattern emerges from the interaction between Saturn's rotation and the sharp difference in wind speed between the pole and the surrounding latitudes. A standing wave locked in place by rotation, rather than a storm in any ordinary sense. Nobody fully agrees on the precise mechanism, and no other planet in the solar system has shown anything like it at either pole. Jupiter, similar in so many other respects, spins even faster than Saturn, and shows nothing resembling a hexagon anywhere in its clouds. A planet's rotation, it turns out, doesn't only speed things up or flatten them into disks. Occasionally, applied to the right fluid at the right latitude, it paints a shape stable enough to outlast every spacecraft we've ever sent to look at it. Each side of the hexagon is long enough to swallow Earth's entire diameter, and the whole structure rotates in near-perfect lockstep with radio emissions coming from deep inside Saturn itself. A signal astronomers use as a rough proxy for the planet's true interior rotation rate. Since Saturn, like the Sun, has no solid surface to simply watch turning, that detail matters more than it first appears. It means the hexagon isn't drifting independently of the planet underneath it, carried along by winds alone. It is locked to something at Saturn's very core, a shape sitting at the intersection between the deep interior and the visible cloud tops, holding station for as long as we've had the instruments capable of noticing it at all. Cassini, the spacecraft that spent 13 years orbiting Saturn before deliberately diving into the planet's atmosphere in 2017, captured the hexagon in its clearest detail, yet during its final years, time-lapse footage showing individual storms circulating along each of the 6 sides, like traffic looping around the edges of a 6-lane roundabout that never breaks down and never gets rebuilt. Nothing else in this solar system has offered up anything resembling it on any of the other giant, fast-spinning worlds we've mapped. Whatever combination of rotation, speed, and internal wind shear paints a hexagon rather than a circle, Saturn appears to be the only planet in reach of our spacecraft that happens to sit at exactly the right settings for it. Every other giant planet we've photographed spins just as fast, or faster, and produces nothing but ordinary, shifting turbulence at its poles instead, with no 6-sided pattern anywhere to be found. Remember the promise you heard earlier tonight, that a pulsar's spin rivals the best clocks human engineers have ever built. That promise has one strange exception, and it happens without any outside cause at all. Every so often, with no warning and no external trigger, a pulsar will suddenly spin very slightly faster than it did a moment before. A glitch, astronomers call it. A sudden speeding up in an object whose entire reputation rests on never speeding up, unpredictably. The jump is tiny, often less than 1 part in a million, but it happens instantly, within seconds, in an object that should only ever be slowly, gradually losing rotation to the same radio wave beam that makes it visible in the first place. The leading explanation lives entirely inside the star, in a place no telescope can see directly. A neutron star's outer crust is rigid and locked to the rotation we measure from outside, but underneath that crust, physicists believe, a form of matter that flows with zero internal friction, spinning at its own pace, slightly faster than the crust above it, like a hidden flywheel storing extra rotation the outer shell has already lost. Every so often, the theory goes, the crust and the inner superfluid abruptly lock back together, and the faster spinning interior hands a sudden jolt of its rotation to the slower crust we're watching from Earth. The entire glitch finished before the signal announcing it has even fully left the star. We have never directly observed the interior doing this. We have only ever seen the outer shell announce, instantly and without warning, that something underneath had just changed its mind about how fast to spin. The most famous glitching pulsar sits inside the Vela supernova remnant, the wreckage of a star that exploded roughly 11,000 years ago, and it has glitched more than 20 times since astronomers began watching it closely in the 1960s. Often years apart, with no way to predict the next one in advance. Each glitch is followed by a slow, gradual relaxation over the following weeks or months, the crust and the hidden superfluid inside settling back into their normal, slightly mismatched arrangement before the whole cycle waits, silently, to happen again on a schedule nobody has ever fully deciphered. There is something almost unnerving, if you sit with it, about an object this reliable holding a secret this well. A pulsar's flashes are steady enough to help calibrate spacecraft navigation across the solar system, and steady enough that the pulsar timing arrays we covered earlier could detect gravitational waves using nothing but that steadiness. And yet, every so often, without external provocation, it reveals that its own interior has been quietly disagreeing with its own exterior the entire time. Patiently, invisibly, for years between each confession. The clock we trust to calibrate spacecraft across the solar system is, underneath its own perfect surface, still arguing with itself decades into being watched closely, and shows no sign of stopping anytime soon. You don't have to look at a dead star to find an interior secretly disagreeing with its exterior about rotation. There may be one buried under your own feet. Earth's solid inner core, a ball of iron roughly the size of Pluto, floats inside a churning outer core of liquid metal, mechanically decoupled from the rock above it, free, in principle, to spin at its own slightly different rate. For decades, seismologists have tracked this by timing earthquakes that repeat at nearly the same location years apart, listening for tiny differences in how long it takes their waves to cross the deep interior, a difference that shifts depending on exactly how the inner core happens to be oriented at the time. In 2023, a team of seismologists published an analysis of these repeating earthquakes going back to the 1960s, and concluded that the inner core's rotation relative to the rest of the planet had gradually slowed, paused around 2009, and appeared to have begun drifting the other way since. The core, in effect, gradually falling out of step with the mantle surrounding it, then falling back into a different step altogether. Other seismologists studying the same public earthquake data have pushed back on the exact interpretation, arguing the core might simply be wobbling or deforming at its surface rather than truly reversing its spin. The debate remains active. Unresolved, argued from the same limited set of confirmed data by researchers who agree on what they measured and disagree on what it means. Whatever the correct interpretation turns out to be, the deeper point survives every version of the argument. Fewer than 2,000 miles beneath the ground you are lying on right now, something roughly the size of a small planet has, at some point in your own lifetime, either slowed, paused, or reversed a rotation nobody outside a seismology lab will ever feel directly. Your own sense of a perfectly steady, unchanging Earth turning beneath you has never once required the deep interior to agree. No earthquake shook harder because of it. No day measurably lengthened or shortened on any calendar you've ever owned. The entire disagreement has been unfolding in a part of the planet no drill has ever come close to reaching, detectable only by comparing the faint arrival times of seismic waves from earthquakes that happen to repeat in almost the same spot, years or decades apart. It is entirely possible to spend an entire human lifetime standing on a planet that is quietly renegotiating its own internal rotation and never once have a reason to suspect it. The planet you were born on and the planet you will fall asleep on tonight are, in this one narrow respect, not quite the same object underneath your feet, and the difference has never once interrupted a single sunrise or kept a single person on the surface from falling asleep exactly on schedule. Tonight included, whether or not they ever hear about any of this. Every rotation you've heard about tonight has assumed its galaxy gets to keep spinning undisturbed for as long as it likes. Your own galaxy, the Milky Way, does not have that luxury indefinitely. Andromeda, our nearest large galactic neighbor, is falling toward us. Not drifting apart the way most distant galaxies are, carried along by the universe's overall expansion, but genuinely approaching, gravity winning decisively over that expansion at this particular short distance. Current measurements put the two galaxies on course to begin merging in a little over 4 billion years, long after the Sun has swollen into a red giant, but before the last light in the universe finally goes out. Here's what a collision between two spinning disks actually does. And it isn't the head-on collision the word collision suggests. Stars are so sparsely spread out, even within a packed galaxy, that direct star-on-star impacts will be almost vanishingly rare. What collides, violently and completely, is the shape. Two flat, orderly disks, each still carrying the conserved spin of its own individual origin billions of years ago, will tidally distort each other beyond recognition, fling long streamers of stars out into intergalactic space, and eventually settle, over hundreds of millions of years, into something astronomers already have a name for: a single elliptical galaxy, roughly spherical, with no clean disk and no single, orderly spin left at all. Every quiet, patient rule of conservation we've traced across this entire episode, the falling, the flattening, the speeding up, will run, once, in reverse. Two disks, each individually obeying the ledger perfectly, will meet and erase each other's tidy geometry in the process, leaving behind a galaxy that no longer remembers which direction either of its parents used to turn. Simulations of the merger, run forward across supercomputers rather than observed directly, suggest the two galactic cores and the supermassive black holes each already carries at its center will spiral toward each other across hundreds of millions of years, gravitationally slinging enormous numbers of stars onto wildly altered orbits along the way, before the two black holes themselves eventually merge into one. A collision not unlike the one detected by that first gravitational wave signal in 2015, just almost inconceivably larger and almost inconceivably slower to arrive. Whatever remains afterward, astronomers have already given it a name in anticipation: Milkomeda. Any observer alive to see the finished result billions of years from now would find a galaxy with no clean spiral arms left to speak of, its stars settled into a broad, gently rotating haze rather than the crisp, flattened disk either progenitor once maintained so precisely. The very disk shape we spent tonight tracing back to a single collapsing cloud is not, it turns out, a permanent inheritance. It is a phase, an extraordinarily long and stable one, but a phase nonetheless, waiting patiently for the right collision to come along and end it. 4 billion years from now, whatever is left to notice will be living inside the answer to a question this entire episode has been building toward. A spinning disk is not a destination. It is simply how falling matter looks while it still has the shape left to show for it. Every rotating thing we've followed tonight, no matter how far apart the numbers made them feel, traces back through the same handful of steps. A residual drift too small to measure, a collapse that had nowhere to put that drift except into speed, a shape that had no choice but to flatten, Earth's rotation, the Sun's slower one, Jupiter's outsized share of this system's spin, the 700 times a second scream of a pulsar, the forced, dragged spacetime around Cygnus X1. Every one of them is the same handful of steps, run at a different mass and a different scale. Nothing more. That includes you. The calcium in your bones and the iron carried in your blood were forged inside stars that finished burning long before the sun existed, scattered outward by explosions violent enough to briefly outshine their entire home galaxies, and gathered back together by the same collapsing, flattening, spinning up process that built every planet in this story. The spin of the cloud that became the solar system is not a metaphor for your own origin. It is the literal, physical origin of the atoms currently holding this thought in place. You did not arrive in a universe that happens to spin. You arrived by way of the spinning. Consider everything that had to conserve its rotation correctly, in sequence, for that to be true. The cloud had to carry a residual drift. The drift had to survive collapse without cancelling out. The resulting disk had to hold its shape long enough for planets to condense inside it. In the same plane, largely in the same direction, a rocky world had to end up close enough to a stable star for liquid water, and far enough from its neighbours to avoid being flung back out into the collapsing disk before it finished forming. None of these steps required your existence specifically. Every one of them was simply the ordinary consequence of a mass of matter falling and refusing to stop turning while it fell. An accident, if it is an accident at all, that this documentary already promised not to resolve for you tonight, and won't, no matter how many times the same quiet question comes back around. 4.5 billion years of falling, flattening, and speeding up, and the end result, tonight, is a single listener, still, breathing, warm, held together by exactly the same law that shaped everything else in this story. Whatever is true about the deepest, still unresolved questions from tonight, the galaxy alignments, the faint whisper in the oldest light, whether any of it points to something beyond ordinary physics, or is ordinary physics all the way down, this much is no longer in question. The same rotation that shaped a dust cloud 4.5 billion years ago is the reason there is a you here at all, lying still, listening, carried by a planet that has never once, not for a single second since it formed, agreed to stop turning. So here, finally, is the answer this entire night was built to reach. Not a single cause, but an accounting so consistent it stopped feeling like coincidence somewhere around the second hour. Nothing keeps a proton, a planet, a pulsar, or a galaxy spinning, in the sense of some outside hand pushing it along. Something simpler and stranger is true. A universe made of falling matter cannot help but conserve the smallest residual drift it started with, cannot help but speed that drift up as it collapses, cannot help but flatten into disks, and spin those disks faster still. At every single scale we have ever managed to point an instrument at, from the fluid in your own inner ear, to the black hole photographed for the first time in 2019, to the two colliding singularities that finally let us hear gravity itself ring. The universe doesn't need a reason to keep spinning. It only ever needed permission to fall, once, and it has been falling, and therefore turning, ever since. A spinning object, we can say now with the whole night behind us, was never truly a thing that started turning. It is a thing that is still falling, just falling in a circle instead of a line, and has been falling that way since before there was a word for either. Nothing ever had to spin, and nothing, once it learned how to fall that way, has ever fully agreed to stop. And that leaves the largest version of tonight's question exactly where we found it, on purpose. Whether the faint alignment of galaxies across the cosmic web and the fainter whisper sitting in the oldest light in the sky are the same familiar accounting operating at a scale too vast for us to fully verify yet, or a genuine seam in everything we think we understand. That is not something this documentary is going to resolve for you tonight, because nobody has resolved it for themselves either. We are, all of us, still sitting inside that question, the same way a spinning galaxy sits inside the dark matter halo, holding it together without ever once showing itself. Newton wondered what the water in his bucket was spinning relative to. Gödel wondered what would happen if enough of a universe's matter spun the same way. Somewhere between the two of them sits the honest answer available to us tonight. We know, in exhaustive, tested, repeatedly confirmed detail, how spin behaves at every scale we can reach with an instrument. We do not know, and may never know, whether the largest pattern of all is the same law completing itself or the edge of a law we haven't found yet. Both possibilities have sat quietly underneath everything you heard tonight, unresolved, the entire time. We've drifted through the smallest scale in this story and the largest one tonight, from a single, silent proton to a filament of galaxies hundreds of millions of light years long. And at every stop along the way, the same quiet law was waiting for us, patient, unchanged, indifferent to whether anyone was listening. But so is this. Every one of those turning things, from the fluid behind your own ear to the light of a supermassive black hole photographed for the first time in human history, is part of the same unbroken chain that produced you. Tonight, here, still, the universe was never spinning out there, apart from you. It has been spinning you all along as one of its own moving parts. If your eyes feel heavy, let them close. That was always the plan for tonight, and nothing about drifting off partway through counts as leaving early. If this felt like the kind of night you return to, leave a comment when you wake up and tell us where you drifted off. And if you're still here, still listening, the universe has plenty more of these nights, waiting whenever you're ready for the next one. You are lying still, Your breathing has slowed, and somewhere underneath that stillness, carried sideways through space at 1,000 miles an hour, on a planet that has never once stopped turning and never will, not on any timescale that will ever concern you. The universe will still be here when you wake up. So will we. Good night.